Okay, sorry about that little hiccup there. So what we have to do is figure out what what our new limits of integration are. So this was over x, so we need to plug these back in. So we'll plug 0 in for x, and then take the cube root of it, and then take the arc cosine. And so when is cosine equal to 0? That's at pi over 2. And then we can plug the 1 in and take the cube root, it's still 1, and say when is cosine equal to 1? And that's at 0. We can actually get rid of our negative by flipping that. So this will become 0 to pi over 2. And then we can get rid of the negative that was in front of the 3 here. And what we end up with is sine cubed of t times 3 cosine squared of t sine of t dt. And then what I want you to do is go ahead and go to page 673. Well, first I want you to try doing this integral on your own and see if you can work this whole thing out. If you can't, then go to page 673 in your book, and it goes on and over to 674. And I want you to try working this integral out just as a little bit of practice for you. And then you get it all evaluated and everything, and you should end up with a 3 pi over 8. So I won't make you watch this in video, but if you need me to go through it with you, I can in our next meeting. But give it a try. Try it, and then check out page 673 if you're stuck, and look at what they're doing. If you're still stuck, just let me know. So go to page 673 and 674 and take a look and see if you can get that to work out. All right, so next part is the length of a parametrically defined curve. Earlier we learned length of the function is given by this. Well, I'm gonna kind of do this a little differently than the book does. You can look in the book if you don't like my method, but I'm not a big fan of the way the book does it. It's very kind of meticulous, and I don't think it's super intuitive. What I want to do is say, okay, I've got, and actually I'm going to pretty much skip this one altogether because this is just a special case. This is just a special case when you parameterize it in that super simple way, like we did before, where you just make x equal to t. And so anyway, you end up with this. That's a special case. So let's take a look here. And let's say we're looking at a curve right here. And what we're going to want to do is look at, this curve right here. And each one of these little sections of the curve, let me get a color here. Each one of these sections of the curve is a little arc length, little s. All right, and it's a little s. All these little arc lengths, S1, S2, S3, so on and so forth. And we can approximate them by making these straight lines that you see there in red, and we could go through and add them up. And if we take the limits of those little points that we're connecting like that are all right next to each other, we essentially have something really close. And so if we take a look at that, we want to figure out what's the length of these line segments that are right here. Let me do that. So this is one of our little s's, and we want to know what is the length of this line segment right there for it. And for that we can do Pythagorean theorem, and we can say that our s value, s, is going to equal, and what it'll be is just Pythagorean theorem, delta x squared plus delta y squared. And so what we want to do after we have this idea is, what we want to do is take those s's, make them infinitely small, and add them up. So we're going to take that limit that we're going to do, so our total length of our line length, let's call it, is going to essentially equal the integral of, we're going to sum up all of those infinitely small s's. We're making these s's, into little teeny tiny ds's, and we're going to sum them all up. And so if we look over here, what we can do is kind of change this from delta x's, and we can make this a ds, right? This is the ds here that we're doing. And then our deltas become dx's. And we can replace this over here with integral, and oops, I forgot just a minute ago to put squareds on these. And then we can take the square root to just get ds. So we can have the square root of dx squared plus dy squared. I know I'm kind of squishing this in there, but here, we'll zoom in over here. And then what I'm going to do is I'm actually going to multiply by 1. I'm going to multiply because these are parametric, so we need something with t in them. So I'm going to multiply by dt over dt, because that right there, that form right there, we're not going to be able to integrate, plus dy squared. And then I'm going to take the denominator dt and I'm going to put it inside the square root. And in order to put it inside the square root, I have to square it and take the square root of it. So what I'll have is dt times, and I'll have 1 over dt squared times dx squared plus dy squared. And then I'm going to move my dt to the end, and I'm going to get square root, distribute my 1 over dt squared, dx squared over dt squared plus dy squared over dt squared. So thinking of it this way, and then integrate over dt. And so basically, this is the length of any individual little teeny tiny little segment. That's these little segments here, so it's the length of this, but in the limit that each of these lengths, goes down to being infinitesimally small. And then I'm going to sum them all up, and that's through my steps dt. I'm going to take a step in dt, and then I'm going to have a dy and a dx. So essentially what I'm going to do is take a step in dt, I'll get a dx, and I'll get a dy, and I add them together, and I get that length right there, and then do it again. I take another step, and I'll get another dy, and a dx, and a dy, and a dx, just like that, all the way through a bunch of dy's, dx, add them all up, and that's essentially what we have here. So that means if we want to find the length of a parametric curve, we can simply do the length of the curve is equal to an integral from a to b, wherever we're starting, point A to point B here. We can integrate from a to b, and we can just do the square root. So it's just Pythagorean theorem, dx dt squared, so the derivative, plus dy dt, and squared. So you're going to take each derivative with respect to t, square them, add them together, take the square root, and then integrate. And that's basically what's going to do it for us. So let's try and take a look at one of those now. And so what we've got on the next page here is, using the definition, find the length of the circle, the radius r, parameterized by this, and we're going from 0 to 2 pi. So we're only going to go around once. We're not going to come back around on ourselves or repeat or anything like that. And we're just going to get this length here. So remember our L, we're going to integrate from 0 to 2 pi. That's where we're going on t. We're going to do the square root of dx dt, so the derivative with respect to t of x, plus the derivative of y with respect to t squared, square rooted dt. So we need to find dx dt. That's going to be the derivative of this up here, and derivative cosine is negative sine, so this will be negative r sine of t. And then y, or dy dt, is the derivative of y with respect to t, and so that's going to just be r cosine t. And then we can square both of these things, squared, squared, square it, square it, and go ahead and put these together, and what we'll have is L, okay, is going to equal integral from 0 to 2 pi, and when we add these two things together, we're going to have r squared sine squared and r squared cosine squared. So I'm going to factor out that r squared out front, and then I'm going to be left with my sine squared t plus cosine squared t, and don't forget when we squared this became positive. Okay, and so we have r squared times sine squared plus cosine squared, and we're integrating over dt. And then we have to actually take the square root of this. But sine squared plus cosine squared, that just equals 1. And so this will equal the integral from 0 to 2 pi of the square root of r squared dt, which then when we actually do the integral, all right, r isn't, it basically r can, the r, when you take the square root of r squared, the r can come out front, and we have r times, essentially just the integral of 1, which is t, from 0 to 2 pi, and this will be 2 pi r. And there we go. And this should make sense because this is the equation here for a circle, okay? Which is why we ended up getting what we had there. And this is the distance around a circle of radius r. And so that worked out pretty well for us. And if you're not sure about that, remember x squared plus y squared equals r squared. And so this would be r squared cosine t, you know, just go through and plus r squared sine squared of t equals r radius squared, and then you can factor that out and you'll get, you know, basically just r squared equals r squared. So this works perfectly right there for a circle. Okay? All right. So next thing, let's take a look at example here, and we want to find the length of that of this curve here now with the asteroid. But whereas before we only found the area inside of it. So let's take a look here and see if we can go ahead and do that here. Okay, so let's go ahead and start that. So we've got to essentially find the length of this part right here, okay? And we can do that here. So let's start with dx dt, and that's going to be 3 cosine squared t times, so that's our chain rule, bringing it up front, and then times the derivative what's on the inside. The derivative of cosine is negative sine of t, so this will give us negative 3 cosine squared t sine t, and then dy dt is going to be, do the same thing, but we're going to get 3 sine squared of t times the derivative of sine, which is cosine of t, and so that'll give us 3 sine squared t cosine of t, okay? And now we need to square each one of those, so dx dt squared is going to be 9 cosine to the 4th of t sine squared t, and then this one squared, dy dt squared, I'm going to run out of room here, is 9 sine to the 4th t cosine squared of t. And now we can add them together. So let's do dx dt squared plus dy dt squared, and you end up getting 9 cosine to the 4th t sine squared t plus 9 sine to the 4th t cosine, sorry, I'm squishing it there, cosine squared of t. And then we can take that and we can actually factor out a 9, a cosine squared of t, and a sine squared of t from everything. And if we factor that out, we get this times, and what's going to be left is, from here, the thing that's left is a cosine squared, and from here, the thing that's left is a sine squared. And when that happens, this is just 1. And so this will just end up equaling 9 cosine squared t sine squared t. Then